of all, let's write down the commutative property of addition is here and multiplication is here. And then I'll give you some examples. Let you jot that down. Now that's not like community. It has no N. Commutative. Commutative. These are guys that might help you see better. The commutative property deals with order. So order is the key word. That's the purpose of this long order right here. It's the key word for telling us that you have the commutative property. For example, when you were in the first grade and you learned that 3 plus 4 is 7, you did the threes that week and you learned 3 plus 4 is 7. The next week, when you had to learn 4 plus 3 was also 7, you're like, great, I already know that one. By the time you got halfway finished up to the 5s, 6s, you already knew half of what you had to learn that next week because it just kept turning around and using the commutative property. 6 plus 7, 7 plus 6, same thing, right? So the commutative property is what that work does. It doesn't matter what order that you add. It also doesn't matter what order that you multiply. Got to the 3rd grade. Started learning multiplication tables. You said 3 times 4 is 12. Next week, oh cool, 4 times 3 is also 12. And the purpose or the reason for that is because of the order. Doesn't matter with the commutative property. Alright, so let me ask you a question. Does the order matter when you subtract? Yes, it does. So there's not a commutative property for subtraction. Does the order matter when you divide? Yes. So there's commutative properties for addition and multiplication. And that has to do, the key word for commutative is order. Alright, next, I'll let you write down the associative property. These are just big raised dots. I kind of exaggerated them a little bit much there, but they're just raised dots. Associative property, again, of addition and multiplication. Let's write those down. Alright, the key word for the associative property is grouping. If you'll notice A, B, C, A, B, C, A, B, C, A, B, C. These are in the same order. The parentheses move in how you group things. So I'm going to stick some numbers in the place of those letters. And then put parentheses here. And then remember parentheses and group them differently and put parentheses there. Alright, now according to the order of operations, what do we do first? Parentheses. So 3 plus 4 is 7, and 7 plus 5 is 12. Alright, so remember the 12. Alright, go over here, 4 plus 5 is 9, and 9 plus 3 is 12. Same answer, right? So it didn't matter how we grouped. Alright, same thing is true as multiplication. Okay, 3, 4, 5, 3, 4, 5, same order. But let's look at the grouping. 3 times 4 is 12, and 12 times 5 is 60. Remember the 6? 4 times 5 is 20. 20 times 3 is 60. So does it work yet? The grouping doesn't matter because of the associative property, and the order doesn't matter because of the commutative property. Okay? Now, if I were you, I would copy down these examples with the numbers also, because when we have quizzes and things, I'm going to give you numbers and may give you variables too, okay? So it'd be kind of a mixed up thing. Alright, distributive. I want y'all to copy that down. Distributive property. Now this is candy. Distributive property is how I remember, or candy is how I remember the distributive property. If I had a giant basket of candy, and I said, I'm going to distribute this today to the class, and I come over here and I give every bit of it to Andrew. Andrew is the only one happy. Is that what distribute means? What do you think distribute means? What would you assume? Would I give 1 to Andrew, 2 to JJ, 3 to John, or 4, and 5, give 6 to you, 7, 8, 9. Then when I finish, I'd have all this left, and I'd just give the whole thing to Dakota. Whatever's left, I'd give the whole bag. That'd be what I would do with you. But is that still fair?
Yes.
What do you think that means? Should I give everybody, if I'm going to do distribute, I would need to give everybody what? The same way. Treat everybody the same way. It would be fair if I didn't. So if I started out giving one piece over here, give one piece to everybody in here, okay? And start out giving 5 to him and give 5 to everybody. Do the same thing for everybody. So when I think about candy and distributing it out fairly, the distributed property means this. Now notice, over here, my multiplied number's on the left. Over here, my multiplied number's on the right. And it didn't matter where it was. There's always going to be either a sum or a difference, in parentheses. And all we do is take that number on the outside and multiply it by whatever's on the inside. A times B, A times C. A times B, A times C. B times A, C times A. Hey, what property says B times A and A times B are the same thing? What property says A times B and B times A are the same thing? We just talked about it. The order is what? Commutative. Okay? Now you guys did the distributive property today in the bell ringer, didn't you? 3 times x and 3 times -2. 2 times x and 2 times 4. That is the distributive property. You take whatever's on the outside and multiply it by everything on the inside. Now what people do, even in pre-calc, you'll have a problem. And they'll remember to multiply the first term. And then the second term, they'll just bring it down. What they forget to do. They forgot to treat everything fairly. 3 times -2 also, right? 3 times everything in the set of parentheses. But I'm telling you, that is the distributive property, easy to understand, but also easy to mess up because we get in a hurry. So everything inside the parentheses is multiplied on the number on the outside. All right, now let's talk about properties of equality. There are 4 of them. Let's you copy that down. All right, so when you look in the mirror, whatever's here is there. It's a reflection. It's the same thing, okay? So I think of that when I think of the reflexive property. All I'm trying to do today is give you things to help you to remember stuff. Sometimes you have to do something interesting to click in your mind to help you remember the reflexive properties, like looking into a mirror and seeing the reflection. It's saying that anything is basically equal to itself. A is equal to A. You might think, well, that's common sense. It is. Everything's equal to itself. You don't even have to tell a first grader, well, 5 is equal to 5 every time. Let's know that, don't you? Then you get into geometry. And you got this figure. Let's say we have a triangle. And in that triangle, we've got this line that separates our triangle into 2 little triangles. I'll call this one triangle ABC and this one BCD. And we're trying to prove that these 2 smaller triangles are congruent or equal to each other. Well, I know that side AB is equal to side BD, and I know that AC is equal to side CD. Well, how would I know this shared side is equal to itself? By the reflexive property. See, common sense even has to have a reason, because everything we do in math has got some property or some kind of rule that backs it up. And so this is saying BC is equal to BC. So did you guys prove triangles were congruent by side, side, side in the 8th grade, or side, angle, side, or angle, side, angle? Those are the ways that we prove triangles are congruent. So hopefully you have some background in that. But in geometry, we use the reflexive property a lot. Talk about segments equal to itself and angles equal to itself. Maybe a triangle equal to itself. But also, you know, there's equal to itself, right? We know that. Common sense. Like I said, first grader, we understand 7 equal to 7 and everything. Because it always says, you know, same fingers on it. Show it 7 equal to 7. All right, the symmetric property. Let me copy that in. Probably when you've done geometry in the past, you talked about lines of symmetry. You talked about taking a sheet of paper and folding it and having a line of symmetry, something that cuts something in half. Y'all remember symmetry, cutting something in half? And this one even has another line. This is a rectangle, and so see, it has 2 lines of symmetry. I could also cut it this way, and it would be half that way also. Think about the human body. If I drew a vertical line down the human body, and then got my eyes are symmetrical, kinda, right? Kinda, my nose, kinda my arms. In case you girls already know this, Because when you look in that mirror, put that makeup on, you notice one eye's a little differently shaped than the other. That's normal. That's the way it is. You guys can check that out. But when you get home, even my hands, when I put my hands together, my right hand is dominant, and I write with it all the time, and it's stronger than my left hand. So I don't know, mine's a little fatter. What about yours? You got one little fatter than me, my wrist a little fatter. But let's just say that they're symmetrical. That the left hand and the right hand meet up. The symmetric property is like this. I could take the left-hand side of the equation and flip it to the right-hand side of the equation or vice versa. It's an if-then statement. See the if? Then? That's called a conditional. I bet you've heard a conditional at home. If you don't clean up that room, then I'm going to do something, punish you some way. Or the other way, it could be positive, you know. If you will do these chores, then you can go to the movies and do so-and-so with your friends. Those are conditional statements. Math has conditional statements too. It's the same, well, if A is equal to B, then certainly I could turn that whole equation around, left-hand and right-hand side, and say that B is equal to A. When you first solved your very first algebraic equation, you probably didn't even know it. You were in elementary school. Now they're doing it down in like third grade. And the teacher got this for the answer, but on your paper you had written this and you were freaking out because you're like, I didn't get what she got. And then what the teacher say, oh, that's okay because they're the same thing, right? Remember that? Well, they are the same thing. Why are they the same thing? Because the left-hand and right-hand side of the equation, the whole thing can be switched around, and that's the symmetric property. All right, call time out here just a minute. What is the difference between the symmetric property and the commutative property? Go back and look at the very first property we wrote down today. The commutative property, how is it different from the symmetric property? Do I have a condition? Do I have a conditional statement with the commutative property? What do I have? I'm either adding or multiplying with the commutative property. I'm either adding or multiplying because remember, does it matter what order you add in? Does it matter what order you multiply in? No. Am I doing either one here or am I just turning the equation around? People get symmetric and commutative confused. But all we're doing right here is saying, oh, well, if it can be this way, then it can be that way. I can just turn it around, okay? All right, let's write down the substitution properties of quality. All right, if you have ever been on a sports team, you understand about substitution property. Raise your hand if you've ever played any sport. Keep your hand raised if you ever rode the bench sometime during that time. If you get to put your hand down, you're lucky. My 9th grade year, y'all put your hands down now. My 9th grade year, I played on the JV basketball team. We went 13-0. We won every ball game. We won the county tournament that year, which in JV is high as you can go at. I was the starting point guard. Man, it was great. It was so good. I was so excited. It was a great year. I still remember all that stuff. I remember the county tournament, being up at Paint Rock Valley, and we were all like this, you know, because we'll be gym. Well, the next year, we had a brand new coach. And she came in, and she had a whole different way of looking at things, and I found myself sitting on the bench. I was starting point guard. Now I'm in the 10th grade, I'm sitting on the bench. What's happened here, you know? Coach saw things differently. But when I got to go in, do you guys think I went in for the center? I'm posting up, I'm rebounding. Y'all look at me. You think I'm the center? I mean, if you're going to put me into the game, I'm going to be in a guard position, right? I'm either going to be bringing the ball down. I might be a shooting guard on a good night. Usually I just point. Just right at the point is all I could do. I'm not much of a, rebounder and that kind of stuff. So why is it that other than the fact I'm short, why is it that they would pick my friend who was very tall to go in for center? Why is that?
They can get the ball easy.
She's more equal to that task, right? I played down low one night against this big old tall girl. and I had to equalize our situation a little bit. All right, so if you're going into the game, you're going in for who you're equal to. You're equal to that task. It's a person who'll come on the sideline, they need out, they need some water. It takes the person that's next best in that spot, they put them in. All right, think about that same thing as substitution problem. A is equal to B. A's in the game. A gets tied. B just goes in, substitutes in. That's all that happens. Now notice that the substitution property's got how many equations in it? 3. Is it also conditional? Look, yes, if. Then. If A is equal to B and then A is used in the equation, then I can take A out, give it a rest, and put B in. We also use that a lot in geometry, but every time we solve a problem, like, what's the answer? 45. I just substituted 45 in for that expression. Why? Because it's equal to 47 minus 2, right? 45 is equal to 47 minus 2, so I took them out of the game, put 45 in because they're equal, all right? All right, transitive property. Let me copy that down. All right, now I've tried through this lesson just to give you things to help you remember, like the reflexive property. What are we going to remember? Looking into the mirror, seeing our reflection. And the symmetric property, what are we going to remember? The left-hand and right-hand side of the equation can do what? Flip around, okay? And the substitution, we're going to remember being on a team and being a substitute and going in for the one that we're equal to. With transitive, here's all I can come up with. Now, this says if A equals B and B equals C, then A equals C. That's definitely another conditional statement. But here's the Sand Mountain English. Do you guys speak Sand Mountain English? You understand some things that we only, those of us who live in Sand Mountain understand? If two things are equal to the same thing, if two different things are equal, if two different things are equal to the same thing, A is equal to B and C is equal to B, if they're both equal to B, then shouldn't they be equal to each other? So if two things are equal to the same thing, then they have to be equal to each other. You know, it's like in geometry. If I have line segment AB, let's see if I can. You just saw me completely duplicate that, right? What does duplicate mean? I made got a copy of it, didn't I? So if I say AB is equal to CD, and then I tell you CD is equal to EF, well, if this is equal to CD, and this is equal to CD, what do you know about AB and EF? They're equal too, right? If two things are equal to the same thing, then they're equal to each other. You guys know any Sand Mountain English? The only people from Sand Mountain know? I'm going to give you one. It's coming up a cloud.
Storm.
It's about the storm. When I was in the 5th grade, that summer, we moved from Chattanooga to Section, Alabama. Yeah, boy. And I remember people saying, well, it's coming up a cloud, and I thought, so what? There's clouds in the sky all the time. What are y'all so upset about? Okay? Now, then, when I moved to Alabama, I learned how to work in the garden. Y'all work in the garden? Can y'all pick beans? Do you hear my y'all? That's Sand Mountain too, isn't it? Raise your hand if you've worked in the garden. Let me see that. What? The rest of y'all need to pick some beans and pick up some potatoes and get okra.
It sucks working in okra.
Okra's hard. You got to pick the love. All right, so I would work picking some shell and the peas. Get purple hands. All right. So when I came here, I would go to my grandparents' house and work in the garden, and my grandmother might say, "I want you to go tote that poke." And I'd be happy to if I knew what that meant. Alright, do what?
I needed a basket full of
The poke is a basket, and if I was going to tote it, what was I going to do?
tote it somewhere.
What am I going to do if I tote it? I'm going to carry it. So she was saying carry that bag of beans or whatever to the house. Alright, so give me some more Sand Mountain. Did you guys know that?
That ain't nothing.
That ain't nothing.
Nick says
over
that like
yonder.
100 times a day.
I can't help
You
it.
got this, but you
I
got
do.
this.
I say
Alright.
that's just my part of
That's what we
it.
talk.
Like you tell him a story and he's like,
Me and my
that ain't
brother.
done. I wonder how my done day is.
I do it.
I don't say done, Nick. I say did it.
Alright, now listen, when I was in college, my mom and dad, my dad's been a car salesman all my life. And he worked in cars all my life. I mean, he has driven everything home, as y'all can imagine, except for, I don't believe he ever drove a motorcycle or 18-wheeler home, but he drove home.
He
Dune
drove a
buggy,
Lamborghini.
gun.
He drove a
It's a
Lamborghini.
sports car. Well, he did drive home a Prowler one time.
Oh, I know we're proud of it.
So anyway, so we go out to Reno, Nevada, and we're going to a car show, and we go to the restaurant, and for my defense, I did have a cold, which makes Sand Mountain English worse. And you told me that, and you're talking, you got the Sand Mountain going.
And they give you your food for free.
No, that would have been rough. That would have been a good story.
They always
Did you
like,
see
they
a
say,
car
I'll give
in
you
the
free
restaurant?
Coke.
Okay, first of all, you don't order a Coke when you go out there.
At work.
A pop or a soda or a cola.
I don't say that. I say Coke. Give me a Coke.
I'll tell you what else you don't, listen, I'll tell you what else you don't order is sweet tea, because they don't even know what you have.
No, they don't even know the biscuit is either.
So I ordered some sweet tea, and the waitress, finally she just makes me mad, because she's like, I don't understand what you're saying. I'm like, sweet tea. She said, wait just a minute. So she goes to the kitchen, and she brings other people out just to hear me say it. Well, this time, I'm like, tell you what, do you guys know how, I try to not say y'all. Do you guys know how to make tea and put some sugar in it while it's still back in the kitchen? We don't do that here. The sugar is on the table. Well, they evidently don't understand that once the tea gets cold, have you guys ever done it? Once the tea gets cold, then you put sugar in, what happens? It just floats around. If we could just teach them.
Try ordering at a drive-thru.
Put the sugar in while it's hot, it melts.
That's all.
Or you
Anyway.
put it in the
Try
water and
ordering
then
at a
put
drive-thru
it
in like Florida.
Biscuit.
Oh,
I see it
it's
like
all right, yes.
One thing my papa learned not to say in Illinois, he was in Chicago, and they were in a restaurant. I think they were in like Denny's or something, and their accent, they talk all proper and stuff, so Papa is from Alabama. He comes up to Chicago to visit somebody. They're in Denny's, and he orders like something, and the waiter like don't know what he said, doesn't know what he said, and my papa looks at him and goes, "Dude, what?" And he goes, and the waiter's like looking at him like he's dumb.
He didn't know what that meant
You don't
either.
say in Illinois.
Do what? We say that. Do what?
Yeah, but go through your drive-thru's worse because they're saying, what? Now I want this.
Have you guys ever gone to Captain D's and ordered rice
Yeah.
and gotten fries?
No, I've actually I've ordered fries and they brought me rice, and they said I couldn't understand if you said rice or fries.
So really, we just need to
I
spell
love
it.
their rice.
Yeah, I didn't. I said, do I need to get a pen and paper and write it for you?
They always get my order wrong, and I get mad and go in there and tell them. They said, I thought you said this.
Alright, let's talk about these.
I've never had a
I go back and.
Alright, while you're copying, let me ask you this. Do you know what identity theft?
Yes.
Okay.
Somebody
Somebody
can
steals
take
your
my
identity, they get your
identity.
credit card, they get your social security
Your money.
number, and they start making purchases in your name, and they ruin your credit rating. And they might even be doing it to you now because you don't know. You don't need any credit yet. You're not buying a car or a house.
That happened to my
So
mom
be
and
careful with,
No, I'm buying a camper.
listen, be careful with your social security number. Be careful with your driver's license once you get that and all those things. Alright, the identity property multiplication says this. Any number that I multiply by 1 gets to keep its identity. Remember that great week in 3rd grade when you were multiplying by 1 and you're like, I got these. 1 times 7 is 7. 1 times 3 is 3. This small case stuff so easy. Then y'all get about 7 and things weren't so pretty anymore. But anyway, if you multiply by 1, the number keeps its identity, stays the same. All right, also, speaking of multiplication, and I hate the way this is typed, so here's the way we'll write it. These are reciprocals. Is that a word you know? Anytime I multiply a number by its reciprocal, I always get what? 1. Think about it this way. What's a half of 2? 1. What's a third of 3? 1. What's a fourth of 4? 1. Anytime I multiply by reciprocals, the answer is 1. So there's an identity property for multiplication. And then multiplying by 1, the number keeps its identity. And there's an inverse property of multiplication. And inverse, there's a key word you want to remember here, is reciprocals. Reciprocals. See, I told you. You think things are just common sense. But even that times by 1 equals the number you start with, it's got a reason. And the reason is the identity property of multiplication. All right, any questions so far? Oh, my mom is right. Okay. There's also an identity property for addition. What do you add to for a number to keep its identity? 0. So that's what we're going to do next. An identity property for addition is when you add to 0. All right, ready? Yeah. Alright, the identity property for addition just says, if I add something to 0, it stays the same. Keeps its identity. Multiply by 1 or add to 0, the number gets to stay the same, keep its identity. Alright, the inverse property of addition, the key word here, instead of reciprocal, is opposites. Opposites. So if I have a number like 7, and I add it to its opposite, -7, I always get 0. If I have a number and I add it to its opposite, I always get 0. So opposites are the key word for the, drink of water, for the inverse property of addition. So reciprocal is for multiplying inverse property, and opposites are for addition inverse property. Alright, questions? Alright, now I'm going to let you write the word closure, and I'm going to describe and talk about closure to the best of my ability by using an analogy.
I heard of
And you can write whatever you understand about closure from what I say, but I need you to use your imagination for just a few minutes, and we're going to talk about closure. All right, many of you have played on a sports team, and you guys haven't, you may not know this, but what is a closed practice?
No one can come in.
The only ones that can come in are the coach,
And
the team, and everybody else has to stay out because we got to focus on what we're talking about, right? All right, so let's say, we got to use a big imagination here, but let's say the whole team is just made up of every number you can think about. All over the gym. There are fractions, there are decimals, there's 0, there's negatives, there's positives, there's pi, there's all kind of, just running all over the gym. And let's say that, excuse me, addition, subtraction, multiplication, division, those are coaches. Okay, so they're running all over the gym. All right, pick any 2 real numbers, any 2 numbers that you know of, pull them together and add them. Do I get another number that's in the gym? Pick any 2 real numbers and subtract them. Do I get a number that's in the gym? Yes. Multiply them. Yes. Divide them. Yes. So we would say that real numbers are closed with respect to addition, subtraction, multiplication, division. All right, so let's do what we would love to do, and let's just kick all the fractions and decimals off the team. They don't do anything but cause trouble anyway, right, for everybody? So let's just kick them off the team. They're gone. Who's left in the gym? The decimals and fractions are gone. Who's left? What do you call them? No. Decimals and fractions are real. I kicked them out. Who's left? Starts with an I. The integers are left. All the whole numbers and their opposites. Okay? So I've got my positive numbers. Now there's infinitely many of them. That's still a big thing. And I have 0, and he's not working on it. Some of y'all get that later. And then there's negatives, and they're all sad and griping all the time, negative about everything. But they're still on the team. Okay? So pick 2 of them and add those integers together. Do I still get an integer? Yeah. Okay? Subtract them. Do I still get an integer? Yeah. Multiply them. Do I still get an integer? But divide them. Nope. 8 divided by 2 is 4. 4 is still in the gym, right? But 2 divided by 8 is 2 over 8. Reduces to 1/4 or 0.25. I've already kicked all the fractions and decimals off the team. So the integers are closed with respect to addition, subtraction, and multiplication, but not division. Y'all still with me? I don't know about you, but I'm tired of listening to the negative gripe and whine all the time. So I'm kicking them off the team. Who's left? And
0.
so what do you call 0 in all the positives? Starts with a W. The what? And the whole numbers start with the number with the whole in it, 0. Alright, so I pick 2 whole numbers, I add them together, do I get another whole number? Yeah. I subtract 2 whole numbers, do I get another whole number? Be careful. 7, sometimes, 4 minus 3 is 1, but 3 minus 4 is -1, and he's gone. So careful. Are the whole numbers closed with respect to subtraction? But are they with addition? Are they closed with respect to multiplication? Could I multiply 2 whole numbers and get a whole number? Yes. Could I divide 2 whole numbers and get a whole number? No. So the whole numbers are closed with respect to addition and that's it. All right, keep 0 off. He's not worth anything anyway. Now what have I got? What do you call all the positives? Natural or, somebody said it, natural accounting. Did somebody say that? Maybe I just heard that. But okay, I've got all the natural or counting numbers. 1, 2, 3, 4. Why do you call them counting numbers? Well, can you imagine a preschooler starting with negatives? How do they learn how to count? 1, 2, 3. They don't even know about 0 yet. They don't get it. Okay? So we call them natural or counting numbers. All right, let's add 2 natural or counting numbers. Do I get another counting number? Yes. Subtract them. No, I might get a negative. Multiply them. Do I get another whole number? Divide them. So the whole numbers are closed with respect to addition and multiplication. Now that's how I understand closure. Welcome to my weird world. That's how I understand closure, okay? So if I could add, subtract, multiply, or divide them and get another one of them, I'd say it's closed, but if I can't, it's not. That's closure. Alright, go to page 87, and in your notes, do these write down the problem and give the property that's being used, and we're going to check it. Okay, let's go over these together. 32 plus 17, 17 plus 32, that is a different order in the way that they were added. So number 32 is the commutative property of what? Addition. How do you know that? Because you're adding. Commutative property of addition. Alright, we ready? 33. The 13 is multiplied by the 21 and by the 9. So what did you say that is? It is distributive. Distributive. And with 34, the 6 is times the 4 times 7 and the 2. So 34 is also distributive. Alright, 35. 4, 5, and X are in the same order. but the parentheses are the grouping moves.
Associative property of multiplication.
So that is the associative property of multiplication. So number 35 is the associative property of multiplication. All right, 36 is so sneaky. It looks distributive, but it's not. The negative 8.2 is on the left, and then they put it on the right, and so they switched the order, which made number 36 what? Somebody said it. Commutative property of multiplication. Now remember, it can only be symmetric if it's in the conditional statement. If, then. Okay? If, then. So this is the commutative property of multiplication. All right, 37. The 5 is multiplied by the 6. The 5 is multiplied by the 3. Give me a guess. Distributive. It is also distributive. Let you copy these down
On the same sheet?
on the same sheet tomorrow. How about that?